thank you for starting me, in case. Oh, no, not that chat. Yeah, look, you all went off before I got to do the attendance list anyway. So I didn't record it. So in future, please, if you're online, stay online during the break so I can record your attendance. I'm not going to spend class time on it, so just because people are sitting here waiting. Oh, share screen might be a good one too. Oh, no, I am sharing. No, I'm not. What am I sharing? The one window. I've gone back to one window. Now I've got to start sharing again. It should be the whole screen. Okay. Now, where are we? Which one? Introduction. Pre-work. Which one? Complexity. Okay. So, any more questions come up? Yeah. Yeah, Ben asked me to put up a poll. So I was doing it on my the reason I was doing it on that computer, maybe if I do it on this one, I can do an app. And my thing was off. Poll, come on. There's nothing about polls. Wrong keyboard. Poll everywhere. This one? That one? Yeah. Polls in a minute. So hopefully, add a team, add to a team. Yep, that one. Okay, I've added it. Now, can you add the question to that, Matt? So if I have a poll, local student in Melbourne. Okay, well then, okay, that's fine. Yeah. Use here. Okay. Team. Well, he's put on here. Yeah, I know why you're doing it, Matt. Well received. Actually received is the question. Oh, where are we? Teams. Where can I... What? Oh, yeah, I don't want to be disturbed. No, you're right. Not in this computer. Polls. Where's my polls? Polls. It's not showing. Oh, I'm sorry. Oh. So I'm trying to put up a poll for you. I have to do it. I did add that. I must have not finished the process. should have a poll up. It's not showing. Okay, look, I'm really sorry. Good idea. Am I sharing? Yes, I'm sharing. I can see that. Where is it? Ask here. Oh, ask here. Where's ask here? Ah, that does not help. How about I get into the right team? Did I put it in the wrong team? Sorry. Yeah, that one. Apps, polls. Okay. Oh, I want to use it now. It's not showing up. Oh, Lucid Charts, good too. Yeah. Share, no. So if I'm in this team, how do I create a poll? Yeah, good, thank you. Okay, where is it? Live. Is it live in the, sorry, I didn't know this. I've never used them before. It's a good idea. Where are we? That's in Teams. I want the team. Where's the poll showing? Where do I show it? Where do people find it? Oh, I know what I want. This one. Marina. Ah, we were, sorry. Marina, yeah. I'm watching the chat. Oh. Okay. Okay. What I'm going to do, can anyone see the poll on the Teams? Not LearnLine Teams, yeah. All is now live. I can't find it. It might be because I've got notifications off. I don't want it popping up all the time. Teams. Yeah, it should be under class recording. Okay, can you see the poll? Look, I think particularly, okay, quiet. One part of this class, yes, is talk to each other a lot, get help. Ben's had a good idea of polling. I can't see the poll, I think, because I've cut off notifications, so I don't get pop-ups on it. Thank you. This confused me about Teams because I go to answer Ask Here and some of the questions have disappeared and I don't notice them. So please answer this. Understood algorithm complexity, big O, and general code requirements for this unit. Most of what was discussed today was not understood to the point where you don't feel confident completing this unit. I do scare people off in the first class. Not intentional, but I go straight into it because it is a difficult subject. You've got to work hard on it. But that's why I step you through fortnightly exercises. You don't fall behind. You don't think, okay, I'll do this next week, because next week it'll be overdue, or it'll be, the next one will be coming up. It's a lot of content, a lot of ideas, a lot of different way of thinking, so I keep trying to reinforce. So it gets reinforced. You're not going to be examined on this week. You'll be examined on this week and next week, where I'll reinforce it and we're doing exercises. So good feedback. Oh, 5. Yep, still halfway. So we're keeping tabs of you. Which actually is consolation for you, those of you who are worried you're in the equal part. Partly because I did have to go through quickly. There's a lot of pre-work and thing, but now I'm going to go over it. And normally I'll do it more together. But this week I wanted to get the pre-work and the ideas out there. And another reason is I frighten you so you will do work. Do wait until week 3. Do have a go at assignment 1. If you're still struggling, then you know you might need to do this later on the semester. We've got a problem that people come in you enroll second semester, this is your first semester. Some of you, hands up if this is your first semester at CDU. Yeah, that is going to be really hard for you because this is a second semester course, actually probably a second year course. So maybe you won't do it next year. That's why we've got that assessment in week 3. Thanks for reminding me, I didn't emphasize this. Okay, it's getting worse. So I acknowledge 50% responsibility for that not being a good figure. Yeah, 50% is my fault, 50% is your fault. Did you do the pre-work? Did you engage, etc.? Did you ask enough questions? Yeah, there wasn't much time for questions on this one. There'll be time more now. And again, I'll stop splitting. I'm just going to have a splitting seminar workshop. I'll try and do it less. So now we'll be doing more questions. Please do ask questions that help you understand. I do know that what I say is not what you hear. You all have your own interpretation of what I'm saying. It'll make sense to some, not sense to others. There is the Ask Here forum. There is your team that will start getting into you so you can start talking to someone who's in the same unit thing. And so Ask Here, everyone's in. Do please ask questions. There are no, as we say, there are no dumb questions. Any question you ask, other people will be asking. Anything that you're worried about, other people will be worried about. And I'm not going to see it as dumb. I'm going to see it as, oh, I didn't teach that well. So I do get frustrated with questions about process. Like, oh, can I email you? No. They're simple answers, that sort of thing. That sort of thing frustrates me because I'm spending time on something that's not the learning. Yeah. So if I get grumpy about that, that's why. So, oh sorry, that's a bad one going up. The bad one's going up and the good one's going down. Yep, it's getting worse. So there's the poll in the chat. Yep, so I will concentrate on that in the next section. Don't laugh, it's mean. Workshop. So hopefully now, yeah, my call's dropped. I'm trying to join with a programmable computer. None of my my chat viewer and my hotspot won't actually work. It's bizarre. So apologies. If I could hotspot, I could get online. At the moment, the network's not allowing me on. It comes and goes, and I can't hardwire here. In my office now, I'm just on hardwire because it's so erratic. Why can't I actually use my data? This is just frustrating. No. Join now. Okay, maybe I can join now. Can't hit it so much. No, stop. It's gone again. Charles Darwin is not allowing me. Which one comes and goes? Okay. If anyone else can run it on their computer, you can share the screen. Okay, so what we've got is GCD examples. So I've got an example where I've written out for you the code that I have. So this is under the repository. So you go to, oh, sorry, where is it? This one. So if you git pull this, if you don't know how to git pull, you go to the actual, just the link for the, oh, sorry, am I sharing screen? Yep. So under here, you've got the link to the repository, or the link, oh, sorry, the link to the repository, or you've got the link to the instructions which tell you how to work on the repository, and use Visual Code Studio, and a bit of instructions for those new to programming. Tell me if they're not helpful. I can add to them. Then I've got links to the code which are under that repository. So you can actually just download that bit of Python and run it under Python. And if I had a computer that would join the internet, which would be so nice, or a phone that would give me internet. Never had that problem again. Why would I not have hotspot? Yeah, it's Wi-Fi, yeah, it's all working, but I can't get a hotspot. Zip, so we've got this code. I get the code, nope, one of these is code, that can go away. So I've set up, oh, that's the other one, factorial, this is, yeah. So this one, I do it to subtract every step. This I do the remainder one, and this I do the extended function. So those are 3 functions I gave in class, and they run. And I give out the extended equation for the modular inverse. This is just to show you there's different ways of doing it. It's not timed. If you go to the factorial one, it is timed. What I'll do is I'll put up a video of me doing that because I've got it here and I cannot join Teams on this computer. My apology. Not something I expected. Oh, have I now got it? You never know. Somewhere during the time I might actually be able to join. No. Get it. But I'll do it next week because it doesn't matter. It's just showing you that it takes different time. So this is the fundamentals of complexity. Depending how you program, the time will be different. But you can, if those are coders, can see how it's set up to time a function, which is useful. Useful to be able to time it. So this is the other thing about learning. Different people learn differently. So if you learn by examples more than by hand waving and theory, then this is more of the examples. So just to get a feel of it, suppose a computer takes 1 microsecond, a millionth of a second, to execute each operation. How long it will take to execute each of the following numbers of operations? So if it's log, is that a 10? No, log base 200. What's log base 2 of 200? I'm not going to hazard it. Google is my friend. Look at that. 7.6. Oh, okay, I got it. So I have, oh, sorry. Yep. I am sharing, yep, the right thing. Good. So how many seconds, microseconds, will it take to compute a function that takes log 200 base 2? Sorry? How long will it take to do that function? So if this is not this is not about big O n. We don't know what big O n is. We just know how many operations it takes. So we don't know what n is, so we can't say it's function n. This is doing 200 log n log 2 operations, and each operation takes 1 microsecond. So how long does the whole function take? .6 microseconds. Yeah, so each operation takes 1 microsecond. So I've worked out, thank you Google, that 200 log 2 is 7.6 approx. So I can say, yep, it'll take I'll look back on it again soon. So I can say that this would take 7.6 steps, and each one 1 microsecond is 7.6 microseconds. You happy with that? B, if it takes 200 steps, how long will it take to do the whole operation? 200 microseconds, which is still microseconds, yeah. What if it's 200 by log 200 base 2? So it's n log n. 200 is n at the moment. You could see the idea I'm looking at. So it's 200 by log 200 base 2. It'll be 2 7 to 14, 15 or so. 15, 1,500, so 1 millisecond, 1.5 milliseconds. Yeah, about. Don't trust my maths in front of a crowd. But yeah. So 1.5 milliseconds. So what if I've got 200 squared operations? That's 40,000, yeah? 40,000 milliseconds, that's 40,000 microseconds, sorry. That's 40 milliseconds. So we're getting a bit of time taken. What if it's 200 to the 2 or 3? 3. Under a 3, that says. That's 800,000. More than that. 8 million. So 8 million times 1 microsecond is 8 seconds. Getting a bit of delay now. And 2 to the 200, I'm not going to bother working out, but obviously it's going to be really slow. So that's the reason we're doing these calculations. And that's for functions of different complexity, obviously, with the same data of 200 data points is what we'd get. So if n is a positive integer, we're assuming that because our data size is n, so it's always going to be a positive integer. Compute the number of additions, subtractions, multiplications, divisions, and comparisons that might be performed when the algorithm segment is executed. In other words, count the operations that will happen. And we're looking at, as I said originally, looking at basic operations. Addition, subtraction, division, multiplication, and comparison are operations that take time. So those are the ones that we take, a microsecond. That's substantial time in a computer. So they take substantial time. So state the order of complexity using big O notation of this one. Now, can you read it? It's the first trick. So for I, it isn't equal, it looks like greater than. For I, I've got my long-sighted glasses on. So. For I equals 3 to n minus 1. So how many steps will I go through? How many times will I go through that iteration? I'll do it n minus 4 times, yeah? So I start through n minus 3 and 4, one of those, yeah. So that's the number of times I'll do that loop. So it's a multiplication by that. And within each loop, how many operations do I do? Assigning, we're not counting assigning. Convention is we don't actually count assignments. The book says differently. My convention is we don't. It doesn't matter either way. So 3n plus 2i minus 1. How many operations in that? 1 multiply, 1 addition, 1 multiply, 1 subtraction. So 4. 4, yeah, so 4. And our 4 I do n minus 4 times. So it's 4n minus 16. And then that's just a loop. So it's just a loop. So it's 4n minus 16. So what's the big O notation? N. N. So you lose the 4 and you lose any, hopefully I've got an example that has to be, yes. So this will be the example of that. So I assign max to the first element, or the second element of the list actually, we'll get into that. So I'm assigning max to A1. I equals 2 to n, how many times do I do the loop? N minus 2, or is it n minus 1? N minus 1 actually, yeah, I knew there was something, we're counting something twice. N minus 1. And in the loop, how many steps do I do? If max is less than AI, then max equals. So that's a comparator, 1 step. And that's an assignment, so we don't count assignments, is the convention I use. There's different conventions, but it doesn't matter because it's a factor that will get cancelled out. So for this one, I'm using this request here that you only use. Sorry, the textbook does include assignments. So this is just 1 step and 1 to n, so it's n minus 1. Sorry, 2 to n, it's n minus 1. And then, so it's n minus 1 plus 1 at the beginning. So that's the number of steps I'll do in that thing. So what's the big O of n minus 1 plus 1? Sorry, n minus 1 times 1 plus 1. The n, yeah. If this was 3 steps, it'd still be the same. So that constant factor at the end gets wiped out too. So don't worry about constant factors or constant multiples. You just get them. So for this one, Anisha, sorry, I did see you. Yes. I mean, now, I didn't see you before. Okay. For online people, and you can't see the online. So for I equals 1 to n on 2, how many times do you do the iteration? Online, tell me. And I'll tell you what they say. If anyone's alive still. Sorry. Hello. You just come through. It's a bit slow. So looking at C, this one. No, that's not going to help. So C. So the number of iterations for I equals 1 to n on 2, how many times do you iterate the loop? Yeah, C. I thought C was not the answer. You're right. So how many times do you do the loop? See, it's very slow online. And there's a problem. If I get comments, often it's delayed anyway, even if I do see them. I see them a bit delayed. Okay, class, how many steps do we do? N on 2. And in each, sorry, how many steps? Sorry, how many iterations do we do? And each step is how many steps? How many operations in that? 1. So it's just n on 2. And so what's the big O of that function? Or that kind of function? N. So it's still n. Halving it doesn't make much difference. It's still n, expands linearly. So yep, it's big O n. Now this one. Number of comparisons in. Yeah, it's not a comparison. Sorry, back to this one. I think it's not. Yeah, it's order n. This is not comparisons. This is. Well, actually, yeah, you do actually do one comparison here because you're comparing. No, you're not. You're adding one to I. So literally, if you want to be pedantic, which I usually am, you will be adding one to I each time. So that's another step. So each loop actually has one step for the iteration of I and one step for the subtraction of 1 from n. Oh, that's an I. That's fine. That makes more sense now. Subtraction of I from n and to get a. So it's actually 2 times 2n on 2, which comes out nicely. Okay, for D, now we've got 2 loops. So you start out with the outer loop. How many iterations of the outer loop? It goes from 1 to n. So the outer loop. So yeah, I'm telling you, stop jumping ahead. Yeah, I'm trying to get those who are not used to it to, yeah, so I'm not saying you're wrong. I'm just saying slow down. So there's n steps on the outer loop. Then you come to the inner loop. There's 2n steps. And then in here, you've got n squared plus I times j. N squared is simply a multiplication plus I times j. So that's 3 operations. And then you have 3 times 2n times n. So it's 6n squared. And this, you just get used to it. If I've got a double loop, that's going to square my n. Yeah? Because I'm going to go through n twice. So that's when you start doing things like we did with that, the average one. You store the total each time so you don't redo it. You don't want to keep redoing your averaging. You just do it once. Once you've got something like a double loop, you know you've got something that's a bit too, go a bit big. You want to reduce it. So this is 2n, what was it, 6n squared, what's the big O? N squared, yeah. I'm going to, oh yeah, this one. So I'll jump down to F. For i's 1 to n, how many iterations? N. How many, then j equals I plus 1 to n. How many iterations? N, well, it's n minus I plus 1, and I is changing. So it's a bit more complicated, but we're doing the big O, the worst case, so we can approximate it by n steps. It's definitely not going to be much less than that. Certainly as I gets bigger, it will reduce. You could probably say it's averages out to n on 2, but it's still big O n. And then within that, you've got, if aj is less than ai, so you've got a comparator, and just see, yeah, and then you've got an assignment, and assignment. So what are you doing? Swap. You're doing a swap. So Python, it's just called swap. You don't have to do all this. So you're doing a swap, which is one assignment really, and we're not counting assignments, so we'll just count the comparator. So it's only 1. So I'm doing one operation within an n on 2 loop and an n loop, which is n squared on 2. What's the big O? N squared, yeah. Everyone happy with that sleight of hand? Did I confuse you more? Do we read? Oh, just check the poll. I've got to check the poll. Okay. Lesson to Kat. Thank you, Ben. Yep. Definitely got to slow down at the beginning. So one more. So 1 to n. There's n iterations. J equals 1 to I plus 1 over 2. How many iterations? And I is a value 1 to n. So I would approximate n on 2, yeah? Or even n on 4. Because what I'm saying is, like at the beginning, I will be practically nothing. But as it gets close to n, or even at half n, it'll be n on 2. So it's getting significant. So I'd say n on 4, say approximately. Then how many operations here inside the iterations? 1, 2, 3. So it's 3n on 2 times n. So 3 on 2 n squared. So the big O is 3 on 2 times n squared. The big O is n squared. Yep, I think it's the same one. 2 to the n. Oh, sorry, Ben, which one were you answering? 2 to the n. Do we get to 2 to the n? Where are you adding, Ben? So Ben, which question was that? You've got, I've seen your answer. F. F, 2 to the n. 2 times, no, it's, so I'll show you this online. Look. So F. So F is saying you get this sum, the number of steps each time. So the number of steps will be n here, and it'll be n times n. So not 2 to the n, but n squared, I think, is the. So you got two times. So it'll be 1 time, when n is 1, it's 1 times nothing. So 2 would be 2 times 2 is 2 times 1, yeah, 2. If n is 3, you'll get 2 times 2, which is 4. And it's 2 to the n steps. Oh, thank you. Sorry. But it's actually n steps. 2 to the r, but we're summing it. It's not 2 to the n. So n is 3, n is 4. We do 4 times. Oh no, I'm just counting individual. Oh, you're counting individual ones, not the whole process. So if n is 4, you'd go 4 steps, and you'd go. You'd step through 1, 2, 3, 4. Which would be 4 times 4, which is n squared. Yep. D, oh, D, you're D. So K equals 1. So you're stepping through. You do your 1 to n minus 1. So you're doing n steps. Oh, you've got an extra step in there. I didn't do E. Oh, you're sorry. D. Sorry, D. So you're doing n steps. So I'm getting questions online, which you might be right. And for each n step, you're doing 2 n steps. So I'm assuming you're saying 1. No. Yeah, 2. Yep. But for each step, so say if n is 4, you do 4 steps there. And for each of those 4 steps, you would do 1 to 8. So it'd be 4 times 8. It's not 2 to the n. So it's 4 times 8 steps. And n is 4. So it's 2 times n squared. I'll have to check your equation why it's not the same. But I think you're doing each loop twice. I mean, you're playing each loop twice. So how about F? You said F was F. So F, you would go. You go 1 to 4. Say just at 4 as an example, and in that you would go. So for every 1 to 4, you would count. You would do. From 1 to 4 operations. So at most you do 4 operations. So it'd be 4 times 4, which is 16. Yeah, n squared. Yeah. Sorry, that's what I thought you were saying 2 to the n for F. Yeah, no, F is 2 to the n. N squared. And the same here. I think you were counting the iteration twice, is why you got 2 to the n. Because iterations each outer one you do n, and then you look at inside the inner one. Okay, I'll do this for this is a better example. Sorry, this one. I'll use this one. It's a bit simpler. So the idea is you've got an iteration you're doing. You can divide it up because think like the computer. Okay, I'm going to do an iteration. I'm going to do it 1 to. So I'm doing G. Yeah. Yeah. So you've got 1 to n, and so that'll be n steps, whatever n is. That's 2. I was nowhere near that screen. That is. Sorry about that. Well, at least I'm watching. Yeah, it does seem to be on a timer, doesn't it? My mic is on a timer. Helpful. So, yeah, Ben, I'll have to check back over that. Hopefully the chat saves, and I'll say how to rethink that logic. But no, it's not in 2 to the n. I'll get you a 2 to the n one. So yeah. Yeah, so I couldn't show his questions because it's. So if you've got one is 2. We talk about log n a lot. It's usually log base 2. But as I showed in that slide about log functions, I've still got it. No, I don't have it. It was on here. Log base 2 is log base 10 divided by log 2. So log 10, 2 base 10. So they're related. We look at log base 2 a lot because a lot of our efficient sorts are dividing things into 2, 2, 2, 2, 2. So you're working in log base 2. So usually the log n is base 2, but it's the same if it was base 10. Same decrease of rise. So log base 2 of 10 is 3.32. That helps. And log base 2 of 10 to the 4th is 4 times 10 base log base 2. So that was a thing I was saying. You should know that. So 10 to the A is A log 10, log 2 of 10, or log of 10 to the A is. So log 2 of 1,000. So 1,000 is 10 cubed. So 3 times 3.32. So log 10 base 2 is 3.32. So 10 cubed is 3 log base 2 of 10. So looking at question 3A. And question B, 10 to the 6th. So the log of that is 6, oh, it is already log, 6 of log base 2, 10 base 2, and so on. So is that clearer? So dealing with logs. And the main reason, it's just bizarre. It's just bizarre. Why can't I? So that's because you're going to need that when you're working the log functions to get an idea of size. And again, we've got a question like that on assignment 1. So that's how you work on them. Any questions about those so far? Okay, so given your answers in question 4, sorry, question 3. Comment on the following. I moved something that was a bit beyond the scope yet. Consider log n base 2. If we square n, by what value does log n increase? Factor of 2. A factor of 2 means a multiplication of 2. A value of 2 is add 2. So increases by a value of 2 would be add 2, increases by a factor of 2, you multiply by 2. So by what factor does log n increase if we raise n to the 10th power? Other people? Yeah, definitely you have to sit in the back row in future. Sorry? Oh, speak louder. Okay, sorry, and I'm moving away from the mic because that's what I tend to do. That's why I got this one, so I can move. I was going to move with that, but it's the internet's so bad I don't want to move it. So sorry. Yep, I'll stay by the mic. So what factor does log n base 2 increase if we raise n to the 10th power? 10, yeah, so factor 10. When n is increased from 100 to, what factor does log n increase? 10,000 million. So that's 1, 2, 3. So 100 to the what is 10,000 million? 100 to the 5, yeah? Because you've got 2 zeros and you've got 10 zeros. So it's 100 to the 5. So log n will increase by 5 because you're already starting. You could say yes from 10 and increase by 10, but because 100 is 10 squared, you divide by 2 and you get the 5. So it's still the same answer. I just like to reassure you. If you went back to 10, you'd increase 10 from 10, but it increased 10 on 2, which is 5 from 100. Yep. That's right, Ben. Oh, I think I know, Ben, what the problem was. You were looking, n isn't, the 2 to the n is nothing to do with n. It's just all the numbers you're looking at were a factor of 2 or a multiple power of 2. I think that's why it was coming out that way. So it wasn't the same n. It was a different n. This is something you've got to look at. Yeah. Yes, but the factor. No, the factor. No, that's the value it increases by. The factor it increases by is the multiple, Luke. So when we ask for the, again, I'm not going to be worrying too much about this, but it is good for you to understand the English used around maths, you know, the jargon, the language. So factor is a multiple. So Luke's given the difference between the two values, and that's the value increase. So the value it changes by is 31, I think, if he's right, whereas the factor is 5. So be careful. Like I'm saying, it's, in a sense, it's another English. It's a new part of English. It's the mathematical English. So it's a different English. Maybe go to the library and get English help. Now ask her about the maths and stuff and some maths example. What does this mean? So Sue can help you on that. Or do ask your team, like, or again, ask here, please. Question like that, oh, is the factor this or the factor that? Give an example, and I think the factor is this, and I can say, no, you're looking at the value, or something like that, like Luke just did. Anytime you ask questions, you will get learning. It's really important to also we're going to show, I'll have to check that. The answers will be shown for the workshops after. So the answers will be up there for you to revise and check. And I show the different ones, the Sydney and thing, because they should have been shown. I thought Legia was going to put them up as soon as the thing's finished. He can do that anyway. Tools for programming. Now the next part is looking at structures. So I think I might better not run to that quite yet. I've got till 12:30. Yeah, okay. So back for questions on questions from book. Oh, I think. Hopeless. So I'm not sure. Oh, these are the questions from the book. Mind if I use the right hand? So if we go to the book, just to confirm, lets you know the book is under the reading list. You should try answering questions in front of an audience. That's why we have the answers, just in case. So you can read online. This is the thing, you don't need a textbook. Lug it around, you've got it online. The uni pays for access. So down to chapter 3, algorithm analysis. If I can, yeah, I can do that. So that same waffle I gave you, and the same time, that's how you calculate time in an algorithm. The slides are from the book. I do that because then you've always got the book to go back. You've got the lecture audio, or you've got the book, you've got the slides written, or you've got the book expansive written. So there's, again, what way you learn. So my first advice is that for that 59% is to have a look at the book and see if that helps. These rules, again, are written there, and examples. Log 2n is log 2 plus log n. equals 1 plus log n by rule 1. So these rules help you calculate, simplify and calculate the log functions. But the other thing too, once you're in complexity, big O notation, we get rid of any factor of 2. The log of it just becomes 1 anyway. So log of n of 2 is log of n minus log 2, log of n minus 1, etc. So the linear function is fn. N log n function we use, the log function. We just missed that. Okay, the log function is also n squared quadratic. Nested loop. The first iteration is 1 operation, the second uses 2 operations, the third uses 3, and so on. And then we get n times n plus 1 on 2, which is that sum I said that you should know. Oh, sorry. Oh, no, we'll come to it. I'll quickly show you before the end. So this is a nested loop. Yes, you'll get n squared on 2. We've just seen some of those. Cubic function again. So we look at polynomials where this is the count. This is the number of iterations in our equation. Somewhere we've got d loops nested. So it's n times n times n d times. So this is the sort of function we can get in programs. Of course, it won't be necessarily visually. You won't see the d nested loops. You'll see there's some hidden loops. We'll show you. That when you start calculating wells, oh, this is an iteration over an iteration, and you're looping, even though it doesn't look like it in the code. But when you try and count out the operations, yes, it is. So the summations. So when we sum numbers to 1 to n, is this n plus 1 on 2 again repeated exponential functions? How we handle them to work out if you've got b to the n squared is b to the n all squared. So it's basically big O bn, b to the n. You don't need it the factor 2 again. Geometric sums and comparing growth rates. So that's what we go through. Asymptotic analysis. What we're saying, all the things about complexity. Oh, so I'm supposed to be getting into questions, aren't I? I'm going through it again. The asymptotic idea, the whole thing about complexity is what is the worst case, and that's the asymptotic analysis. What are you going to arise to but never pass? So you'll always be under that function. You'll come close to it, but you'll never pass it. So that's the asymptotic analysis. Sorry, I'll get down to the questions, which actually, if I go to the next chapter and go back, is the easiest way. I forgot about that.
So when will we know that algorithm is taking like logarithm or something, and when will we know that take like exponential?
I'll have to give you some examples of exponential. But yeah, it's when you do this calculation, you can work out that'll be the other thing about learning data structures and data algorithms is, you know, this algorithm will take an exponential, or this algorithm. So it's more that way. This is for you to start off to make you appreciate, oh, you can count it and get there. So you start to trust me, yeah? When I say, oh, that's exponential, oh, I could count it and get there, but I know that that's been done for me. And that's what I'm saying. All the experiments have done, we've sort of looked at them and seen these operations, that you can add operations and it will be consistent and you can work out the approximate big O. But you want to get shortcuts. And that's what we start teaching is, okay, these operations are exponential, whatever. So makes it simpler. Sorry, and I might have to go back to there. Yep, I'll do that. So if you go to chapter 4 and go back, you get the questions. It's sort of easier. And then I've got to go up there and turn that off. So the C's are a bit more creative. The R's are a bit more sort of straightforward. What I did ask is, 3.5. Oh yeah, this section. I do ask you to consider which questions you want. So before each class, you can go through the questions, have a look at some of them. Can you do them? Maybe you can do them already without the class. If you can't, what questions don't you understand? Or what ones did you find interesting? So you can graph these on logarithmic function and have a look yourself at the slope. We use the logarithmic because logarithmic just shows you the slope, and that's literally what we want. We want how many powers of n are you looking at, and for the big O. Here we look at, we're given two functions, and for A is n log n and B is 2 to the n squared. Find A, which is better than B for some n. So find the number n where A is better than B. Now, great jargon. We don't mean it's bigger, we mean it's less, because it's better. Better is less in complexity. So we're saying, when is the function A n log n less than 2 to the n? What n naught would that be? So if you've got 1, 0, log of 2, and it's base 2 too. So log of 2 is 1, so 16, and log of 2 times 4 is 8. So 16 is greater than 8, so it's not 2. So I'm gonna have to share screen if I do this, but yeah. So I can annotate and write on the thing, but I'd have to reset up on this screen. So that's the step you go through. You say, I'll try 2, I'll try 4, because I've got a log base 2, so I do the powers of 2. Log of 4 is 2, so 4 eighths, 32 times 2 is 64, and 2 2's, 4 4 is a 16 times 2 is 32. Okay, I still haven't done it. So I've got to keep going, increasing n until this log n is greater than 2 to the n squared. I know it will be, because I looked at the graphs before that I showed you. So that's the sort of process you're doing to find. That is more so that you start to feel, yes, this function will eventually be below or above this other function. So you get this understanding of their slope and how they relate to each other. There's also exercise of this, things like expression. So show that the following two statements are equivalent. The running time of algorithm A is always big O of Fn. We can do that where the F has all these constants and variables. Oh, sorry, only one variable n, all these constants. In the worst case, the running time of algorithm is big O of Fn. So big O is also, is the worst case. So big O will be the worst. If Fn is the big O, it's the worst case of itself. So we're saying, so if we say something is big O of some function of n, then it's in the worst case that algorithm is big O of Fn. Or you could say it's always less than Fn. Not really helping this, I think, to get this is all calculations to calculate the actual value of certain functions. I'll do that one, yeah. So if Pn is a polynomial in n, so it's n to any power, n squared, n cubed. Polynomials don't include 2 to the n. So it's n squared and n to some power. Then log of Pn is big O of log n. How can I tell that? I really want 2 screens to be able to chop between them. So this is so what's the log of A plus B? It's like A plus A. No, that's, you can't do it. You can't take them out, the pluses, can you? Nah. Pn. Oh. So log P, the function log Pn will be let's see. The log of Pn, well, Pn will have a function big O of some power of n. Yeah, it will be the highest polynomial value. So big O of P will be n to the k, some k. So it'll be the biggest power of that polynomial. So if big O of Pn is n to the k, what's the big O of Pn, log Pn, sorry. So as P is always less than n to the k log n. So that's what it's getting at, this idea that you can, I was hoping to get the other terms out, but you just have to ignore them. So you ignore them first by taking the big O of P, which will be just n to the k, and then the big O of log n to the k is k log n, which is k, yeah, so it's that value. That's pretty much all we really did today, is this calculation of big O from different functions. So given n element sequence S, I'm going to go into another topic for the last half hour. So I don't want you to miss linked lists. They're really important. Given an n element sequence S, algorithm D calls algorithm E on each element. Our algorithm E runs order of 1 time when it's called on this element. What's the worst case running time of algorithm D? So we got D calls E on each of its elements, and E runs big O of I time on Si. So there's n elements. S has n elements. So from each of the n elements, the E will run big O of the size of that element, which eventually the largest will be big O of n. Yeah. So it's calling it on n elements, and the biggest one will be length n, so n squared. Yeah. And there will be other multiplication factors, things, but basically this is what I call the 2 iterations. So D is calling E, and E is still bounded by n in the time it takes to operate. But it is, so that's a worst case is n squared. Okay, I'm going to go on to the next part because it's an example of using the complexity. So hopefully this will help you too. But again, before next week, please put up questions in the questions for this week if you're still fuzzy about big O's, especially if I keep calling them different things. Oh, Ben, sorry. Yeah. Did you send another poll? Did you? So big, but where are we? No, it's still the same. A and B will be positive numbers, yes. Always, no, they don't have to be, but they were in that example. Yes, sorry. Yep, thanks. So this is, that's not helpful. I shouldn't expand it. Looking at structures. So here's a quick structure example. I think pretty short. You got it? Yep. Okay. Let's see if this works. It wasn't working at home. Yes, it does work. Oh, amazing. Things can sometimes work on this computer. So, as I mentioned, arrays. They're a common structure we use in programming. They're variable size, but you need to specify their size when you set them up. So an array, and this becomes really significant when you start looking at space complexity. Oh, actually, no, time complexity. Yeah. Oh, that comes later. So array-based sequence. Am I on the right computer? No, no such luck, because I'm on a PDF. So Python has these input structures, and other languages have similar things. Sometimes their lists and arrays are different. So there's lists, tuple, string, and arrays to use a sequence. So there's different languages have different structures. So we're looking at the Python because that's what the text is based around, and that's what we expect you to learn. But obviously you might have experienced other ones. So we'll say sometimes they're different. So these sequences support indexing to access an individual element. So I refers to the ith element of the index. And remember, there's a 0 element. That's what I sort of doing. There's A0 is the first element of any list or array. So they use array to represent the list. So this is the problem with Python. The list and the array is the same. So that's why it confuses me. So the array is used to represent the sequence. So it can be a tuple within an array, or a string is an array. So a string, the lazy dog is THELA or space LA. So a string is just an array of characters. So that's how we look at it in Python. And that's the beauty of Python, because you can deal with strings and language really quickly. It's just an array. So this is where I explain, I talk to the computer, and I expect you to talk to the computer. So you're talking to something where the information is stored in bytes in arrays. And it really helps for you to understand what you're talking to. I won't teach you to program Haskell, which would be very good for your soul, or to program machine language, which is even worse. But I do want you to understand what you're talking to, how it thinks, and therefore how you can talk to it. So this is how it stores data in a strip. It's called your hard drive or your solid state drive. And there's a strip or rotating that is just a sequence of bytes. And so that's the array of your data. And so it starts with at 0, and the ith one is here, and the nth one might be up here. If you're going to keep increasing your n, you need to have an array that can increase, and that takes time. So there's an example of a characters, which is a compact array because it's complete, it's full. Also store elements, so you can have the array could store the index of the elements. So A0 is Renee, A1 is Joseph, and so what? So this actual array would just have a number in it, refers to the memory location of the full string. So when we talk about arrays and items array, we don't know what's in that array. And you've got to start getting used to this thing where we gloss over certain features, because what's significant is we're dealing with an array. whether that array is an index to a machine location with more data or not won't matter at times. And we'll discuss when it matters and when it doesn't. Obviously, if you're going to operate on that item, it'll matter because how big it is. But if you're just operating on calling that item and sending it to the user, then it doesn't matter what that item is. It could be an image, it could be anything. So sometimes it's just a key to the other item. So the primary support for compact arrays is a module called array. So this module is like a library in Python. It's not sort of a primitive element. Define a class, also named array, that provides compact storage for arrays of primitive data types. So primitives are like integer, string, pretty much else, whatever. And then it's an array of those. The constructor array, it requires a type code as a first parameter, which is the character that designates the type of data. So you're declaring an array of primes, or a very small subset of primes. So that's how you set up an array in Python. If you're doing pseudocode, you don't have to know that. Aren't you lucky? So that's what I mean. If you're doing this course as pseudocode, all you need to know that in most languages, you need to set up an array and it will be fixed size. In Python, it's typed. In JavaScript, it's not. Things like that are not important. So the typing means you specify what type of element goes into it. So these are the type codes for arrays. Now you have an option of inserting to an array. So you set up an array with a certain number of elements, or you can do, as I had in some of the code, you can set up an array of n zeros. So you know what your maximum n will be, and you set it up all full of zeros, and then you can add an element to the particular ith location. So you've got your array, and you can, because that array sets it up with elements already. Here we can set it up empty with zeros and then start adding elements. So you add O to the ith location there. So that's how we address it. And in the worst case, this takes O(n) time. Why is that? Because we're adding by moving everything up. We're not adding by inserting. So, as it says, so the new element is totally new. We're moving everything else up and adding one here. So we've got to move all these items up. Now, if I add here, you can see I'm moving n items. So each of those steps of moving up one is a one operation, n times, or here n on 2 times or whatever, but basically n times. So it can take order n to insert an item into an array. Not what we want. We don't want every time we insert into an array that it takes order n. Now removal, again, we remove and back. Now the reason I'm going into this is just one example, but it's a very common structure, as I said, we use. And it's not intuitive that we've got these problems already of adding and removing from an array. Because what happens is we don't want an array with a blank here. What is that? It's got to have something there, and we don't. So our data is basically something, we're removing a data point. So we've got to shove everything down, and that takes order n time. So that's why complexity starts becoming important. So the data structure, now we look at space. The data structure is order n. It always will be order n. We're not copying it or adding it. So we're happy that, yep. So the, big O n. The actual space complexity is big O1 because we're not increasing it, not multiplying. Indexing the element at I takes order 1 time. So the indexing means I want to find what the element at I is. That's order 1 because that's how arrays set up to be quick indexing. That's the structure. That's their power, that we can find the ith element in order one time. So you start learning about data structures. Why do we create array as a fundamental structure? So we can index it really quickly, because if we're going to iterate, we want to index. We don't want the indexing to take more than one order one time. If we had a step along the array to find the ith elements, if the computer, not we do, so when we think of it, we think, but if the computer had to do that, it'd be really inefficient. So we say, okay, array is set up so that we can just get an I and go straight to the ith element. But add and remove run in order n time. So in an add operation, when the array is full, instead of throwing an exception, we have to replace with a larger one. And this is the nasty bit. So in add O, without an index, we could always add at the end. When the array is full, we replace the array with a larger one. How large would the new array be? So there's two strategies to increase your array. You can just add C elements, or you can double it. And we double it. We say, right, I don't care if n was 10,000, we're going to double it, because otherwise it gets really quite inefficient. So this is another sort of, oh, thank you, Ultra. It's gone off the screen, but that's because the way I'm viewing the slides. I'm not viewing the slides, I'm viewing them through Ultra. Save downloading. This is another way you can write pseudocode, looking a bit like C. So if T equals S, the length of S minus 1, then I'm putting into the array a new array of size C, or 2n, or of n, sorry. So to do that, for I from naught, so it's saying for I from naught, so what it's saying is I put naught into I and then I proceed. Or here I put a new array into A. So that arrow just means put this into the left-hand side. So I'll put naught into I and do it for n minus 1. SI goes to AI, and A goes to S. So what I've got to do is, where's S? Oh, S. So, yeah, A is the new array. I want to add, I think I want to add at the beginning. So I don't think it's mentioned this, but I'm adding at the beginning. So what I'm doing is I say, okay, I'll create a new array. I'll throw S into it, and then I might have to quickly download it, sorry. So you can actually see it, would be really handy. And it's not a left-hand mouse. More left-hand mouses, please. Yeah, it always comes to these crunches. Okay. See, that looks much more legible. So I do put that into it. Then I put A into S, which is the, I want N goes to N plus 1, O goes to S N minus 1. S is the, I want them in their new array. Oh, I think it's bits. It looks like S is, I'm putting it back into S, but S has got to be bigger by then. So I'd leave it in A. And then I go to, so I've filled up A from N to N minus 1, then I go to N plus 1, and I put O into the final one. Array-based implementation of dynamic lists. The space used by the data structure is, yeah. Now, if I double it, if I do this, if I add a few elements every time I go over the limit, I've got to redo this. So what I'm doing is I'm doing n copies every time I create a new array. I've got to copy the old array to the new array. So on this line here. So I've got n copies. And I'm doing it every time I go over that C value. So I've only increased it by size C. That's a problem. I'll start getting a very slow add action. So what I do is I double it. I don't care if I only go over at 5. I'm going to double it anytime I need to increase it, just to be sure. So it's a more robust way of doing it. So you'll notice that if your dynamic array will be increased by double. Sorry. So we compare these by looking at the time Tn to do a series of add operations. So the idea is we keep adding, tuddle along, and so we start with an empty stack by array of size 1, and we call the amortized time the average time it takes to add to that array. So we replace we replace the array k equals n on c. So if we're replacing it c times every step, and we've got this n, so we're saying, okay, every time we increase the array by size c, instead of increasing it by the full n, we only increase it by the smaller c, then we'll have to do that n on c times for every time we increase by n. So we're doing a comparison. Increase by c, n on c times, or increase it by n one step. So again, we're looking at worst case. So the total time of a series of n add operations is proportional to n plus c plus 2c, etc. So we're keeping adding the extra array on each time, which is c times that, which is c times k plus 1 on 2. Now, if c is constant, the total time of that operation of adding n times is big O n plus k squared, where k becomes n as k, well, k will head up to n. So we call the amortized time the average over n, so it's n squared over n, which is n. This is not important, but it's just the analysis is important, that you see that given different ways of increase, this is why we increase arrays by doubling each time. If we increase by c each time, we'd have to do it n on c times, and it adds up to be k squared, which is n squared at complete, when you've added n time, elements. So the doubling strategy, we add to the array log n times. So this is, yeah, so I was given one example where you have n and you double to n. So each time you'll be doubling. So the total n operations is you start with n, you add 1, which is n, oh sorry, n was 1, you add 2, 4, 6, 8, and you add 2k at the end. So this is my array, flexible, and I start with 1, and I double it, double it, double it. So this is the size of the array, will be this, and the time to add these is 1 takes 2, 4, etc. will be 3n minus 1. So the total time to add to this array goes to 3n minus 1. So Tn is big O of n, and amortized time, you average that over all the adds that we did, which was n, and you get T of 1. So it's more efficient to double. And so in Python, we have a dynamic array class that we can use that does that for you. So you say, you set up your array as a dynamic array, it will resize for you. Just quickly, oh, this is something else. This is data structures and algorithms list. These are all the data structures and algorithms we'll go through in the unit, summarized. And just, yeah, it didn't have it good. So I took out the slides. So that's the sort of things we'll be looking at. And we'll go steadily through. And that's why you see there's a lot of content in this unit, but they're all, I'll try and emphasize each time why we're teaching you this, what is it showing. So arrays was to show you the idea of space complexity, which will space complexity can be a time complexity in the sense of how do you have enough, if you don't have enough space, you've got to increase the space. So they're very strongly linked. but that function array is always ON, or space complexity is order 1, big O1. Just quickly, the complexity table I put here, show you, is much more than you need. Oh no, sorry. The closed forms is in the other unit. I will have to give you the closed forms. I will give them to you, sorry too. These are some complexities. Again, they're there mainly for you to use later. At the moment, you don't know what a red, black tree or a heap is probably, but they are there. So I've developed all the idea, and here's the hash has an amortized one. Do I have a list? A list array, amortized, there. So you'll be learning all this stuff that fills in the table as we go. So you start to get familiar with how to choose what's best in what situation. But just quickly, before next week, please look up graphs. The graphs we look at are not the graphs XY plot or XYZ plot. They're much more flexible. They're a map is a graph. A map is a graph of where people are located or where countries located, or so graph is a much more open concept. So have a look at that. And we'll be looking at recursions and arrays. Recursion is fun. I do hope you like recursion because it's fun and because it saves a lot of space sometimes time. Yeah. Okay, any questions quickly? Sorry, I'm keeping you to the end. I should run the poll again. Oh yeah. Yeah. We don't form the groups. We the poll. So yes. Pen, I think your poll is more directed at me than the students, but yes, I appreciate it. Big O and general code requirements for this unit. Do you understand? If not, put in ask here. Start asking questions. If you don't feel that confident about completing this unit, remember you've got assignment 1 to give you quick feedback. Can you do assignment 1? Ask people about assignment 1. If you get someone explain something, you might realize, oh, actually, that's pretty straightforward. It's not complex when you're used to it. The problem is you've got to get used to it. Same in any maths. Do enough examples and you'll be used to it. It's about familiarity. So have a look at those. And goes on, yep. And think which is the other thing too, because Ben put up the right things. Each week I'll do this. I'll put up the key features of that week. What were the key lessons from that week? Did you get it or didn't you get it? And that's sort of what the quizzes are for too. The quizzes, yeah. The answers for the workshop, yes. I can open them now, sorry. Yeah, I had Sydney to go up earlier so they could be up. I thought they'd be up by now, but they're not. So it should only be available to each campus because you have class different times. Why did you do that? Come on, thank you. So you should see one of them, hopefully. Also, tell me if you are seeing Workshop Answers Sydney rather than Workshop Answers Casuarina, because that's an error on my part, but you should be in the right one. Otherwise, I'll put you in the wrong teams. You don't select teams, I will select teams. So get your pre-week in or you will not be in a team. That's why I'm selecting them. But do please sit, that's what I was saying too, sit down, sit next to people, ask questions. It's not expected that you will know this already. It's not expected that it's easy. It's expected that the information is provided for you to learn. If it's getting too much of a burden, do ask questions, do use the textbook, do use the tutoring. But For questions, oh, the other thing too, I do tutorials, but I've done them and hardly anyone turns up. So I need the class tomorrow, next week, I can't even poll you. I can't even doodle you. I need ideas of what time would be a suitable time. I could do it after class, but I don't think that's great. No, I can't because I've got a next class. I can't do that one. Yeah, it's my class. Yeah, I know, good one. So some other day that I could do a tutorial, it'll be online. So anytime. So think about what time you'd like a tutorial. I guess I can put up a poll of what times I've got free when I find out when my other students are not got me. So do not panic, but do worry. It is hard. Yeah. And it's hard for everyone. Oh, sorry, that's what I was supposed to be showing. It's hard for everyone. Thank you.
So how they can calculate like
Logins come in when you do things like divide into 2, 2, 2, 2, and that's why it's log based too, because you're splitting it repeatedly, and it comes like it, and that's where we start using that calculation of TN again. So we'll do one of those calculations. So they're not so straightforward. These are the straightforward ones where you literally just count and multiply, and it's all straightforward. Then we start doing something that you have to look at the iterations and see what's happening to the value, which is what Ben was doing, but going too far ahead.
Just speak out on the floor.
Oh, thank you. Yeah, so that's bookshop. All right. Ooh.
Okay, thank you.
Okay. I'll take that. Yeah, so we'll get there. Don't want to do everything in first class, people run away. See ya. Oh, you can see both. Maybe I didn't actually log them. Yeah, we should see external. Oh, it's visible. Yeah, sorry, I'm supposed to put release. I'll do that now. Specific members of the group, and that's Sydney. Sorry, that's what I did wrong. Yes, ask.
I couldn't get the attendance because I haven't got it in my phone. So I went to the library and get it, please. So can I get the attendance?
No, it's a bit late. Sorry. That's all right. Look, there's been problems for a few students in the first one. Next week, you'll be right, yeah? Week one's not important. But I'm just asking people so you know that you can do it. Yeah, yeah. Okay, thank you. Yeah, don't worry about attendance this week because online was useless. Didn't show anyone, pretty much. Specific members of a group. Casuarina. Okay, so now you should only see the one. And hopefully the right one. Wow, and that's far out. Oh, sorry. I thought it was from the cabinet. Very soft voice. Thank you. Okay, any more questions online? Oh, yeah, I thought there were 2 polls. Sorry, I didn't see that. Damn. Oh, I'll send it out in a message. It's not showing. Oh, there it is. Sorry. I didn't scroll down far enough. I just saw the bottom of that one. I will send it out. Yeah, the other thing too is a bit too much in the first. Like I do cover a lot of things, but you don't have to get that from the first class because we go over them. But you're right, I'll send that now. Where is it? How can I do that? But if I do, oh, I've got to stop the recording too. See you.